Hi, welcome to the UW Synthetic Biology online series. In this video I want to introduce the idea of bistability. This is an important idea in biology and in synthetic biology. Many people have built bistable systems, and I want to introduce the idea of bistability in this video, and then in later videos we'll go into more depth. So first of all, I want to show you something that's very familiar to you probably, the Humble light switch. So this switch, there's two of them here. One of them is in the off position, one of them is in the on position. So this has two states, off state and an on state. Now if I were to carefully move this switch up, but only moved it up halfway, I could probably rest it halfway. It's a very delicate position. I have to be very careful in positioning it there because it's quite an unstable position. So in a sense this switch has actually three states. It has an off state, an on state, and this unstable middle state. And that's one of the characteristics of bistability. So a bistable system has two stable states, which we can call on and off, and or also low and high, and one unstable state. So how can we make one of these bistable systems, say using a genetic network? Let me show you something related first. So let's draw a little genetic network. So what I'm drawing here is the promoter reading frame that produces a transcription factor P. Let me write that a little better. Transcription factor P. So this is a gene. And I'm going to assume that this gene produces, and all the associated machinery produces P at a constant rate V1, so it's constitutive expression of P. In turn, P gets degraded, right, at a rate V2, and that degradation rate is going to be directly proportional to the level of P, protein P, so K times P. So it's a first order rate law. Now what I want to do now is show you a graph. So I just draw the axes, and on these axes, on the x-axis, I'm going to plot the concentration of protein P, and on the y-axis, I'm going to plot the reaction rate V1 and V2, the reaction rate of the protein synthesis or the degradation rate. Now let's plot V2 first. So V2 is linear in P, so I can just draw a straight line. So that's V2. Okay, so because V2 is proportional to P. What about V1? Well, I said V1 was a constitutive rate, constant, irrespective of P. So to mimic that, I would just put a straight line. So that's V1. So you can see there's this point here, this intersection point, which marks the point when V1 equals V2. And when V1 equals V2, that means the rate of change of P, dP by dt, equals 0, so that means we're at the steady state. Okay. Now if I can drop a line. Let me get a different color. I can drop a line down from here. All right. That is the steady state concentration of P for this system. Now I can move this steady state point just by changing the slope of this line. So if I made it steeper, you notice that the steady state now moves to a lower level, or alternatively I can make the rate constant smaller, and now of course the steady state moves up to here. So I can change the steady state quite readily, but note that there's only one at any given time. There's only one possible steady state. Okay, so this system clearly isn't bistable, because as I said before, a bistable system requires two steady states and one unstable state. Well, we clearly haven't got that here. I should point out that this state is actually stable, and how do I know that? Well, let's say I made a little disturbance in either increasing PSS or decreasing PS slightly, then I could see what happens to that change. Let's say I increase PS a little bit, so if I move up here, I notice that V2 is there now, and V1 is there and V2 there, and that means that V2 is greater than V1. And if V2 is greater than V1, that means the consumption rate is bigger than the production rate. And if that's the case, then P will drop. So if I were to perturb P up, it would actually come back down. Likewise, if I drop P somehow, V1 now is greater than V2, and if that happens, of course, P gets produced at a higher rate, so it goes up, so this pushes it back up. So this state, I can say, is stable, because any change around P will always try to restore it back to this point. Okay. So let me just get rid of some of these. Okay, now let's have a look at a slightly different system. Let me draw the same one as before. Oops, sorry about that. Let's draw the same one as before. Gene producing P. P degrades like that. And again, P will degrade at a rate K times P. But this time I'm going to change the way V1 works. This time I'm going to add an operator site onto here, upstream of the promoter, such that it activates the production of P. So this then is a positive feedback. Okay, so that means that when P goes up, V1 goes up, makes even more P. So you can imagine this is quite an unstable situation. The more P I make, the more P I make. All right. Now obviously there's an upper limit, because eventually the system saturates and I can't produce any more. So let's do the same plot we did before for this system. Let me draw the axes. Okay, so there we go. And again, on the x-axis I'm going to produce P. On the y-axis I'm going to produce V1 and V2. Once again, V2 is just a linear straight line. Okay, it's just a straight line because it's proportional to P. But now we have to decide how to do V1. Let me just mark that at V2. How do we do V1? Well, I know that V1 probably starts low at low P, because there isn't very much P, so there isn't much positive feedback. So the rate is probably low at low P. And I mean, there are various ways I could do this. I could have a line that, let me just draw some. I could have a line that goes up like that, or levels off. Or I could have, if I arrange some cooperativity here, I could have it changing slowly at the beginning, then quickly changing, then reaching steady state. So let me put that one in. I'm going to assume that there's some cooperativity here. So it starts off low, starts rising quickly, and then saturates. Okay. So that one is V1. And you can see probably immediately that there are actually 3 intersection points. These points mark when V1 equals V2. These are 3 steady state points. So this system has 3 possible steady states at a given set of parameters. Okay. So let's look at the stability, say, of this high state. So let me drop down a line. Let's drop down a line. So this is the steady state. So if we're at this steady state, that's the steady state level of P. What I'm going to do is I'm going to perturb P so that I'm going to push it up a little bit. So if I push it up a little bit, you'll notice that, let's draw this up here, you'll notice that V2 is greater than V1. So if V2 is greater than V1, consumption is bigger than production, therefore P will go down. So this will mean that P goes down. What happens if I were to push P in the other direction? If I push it in the other direction, you'll see that V1 now is greater than V2. And if V1 is greater than V2, then P must go up. So this one pushes it back. So this point here is stable. Okay, so whatever perturbation I might make here pushes it back to this point here. The same applies to here. I can do the same analysis here, and you'll see that this one is also stable. So we got two stable states, a low state and a high state. So this corresponds to off and on. What about the middle one? Well, the middle one, again, I can draw a line that marks my steady state level of P. What happens if I perturb P up? If I perturb P up, alright, you'll see that V1 is greater than V2, and if V1 is greater than V2, it goes P goes up. So instead of restoring P back to what it was before, it actually pushes it out even further. In fact, it pushes it towards this stable point. So if I make a perturbation here that's slightly higher than PS, it'll push it to this stable point here. What happens if I push it in the other direction? What happens if I push it back this way? If I push it back this way, I notice now that V2 is greater than V1. And if V2 is greater than V1, that means consumption is higher than production, so the P goes down. So in other words, this will carry on moving this way towards this stable state here. So this state is unstable. So if I make a perturbation above this point, the system evolved to the high state. If I make the perturbation below this point, the system evolved to the low state. So here we have a system that uses positive feedback that has three steady states, two stable and one unstable. Okay, so we'll continue this discussion in the next video. Thank you.